Today we will be talking about curve sketching and how to find the behaviors of a function in order to sketch the graph in 7 steps. Our first example is f of x is equal to 2x cubed plus 9, x squared minus 24x minus 10. The first step is finding the domain of the function, which in this case will be negative infinity to infinity, as this is a cubic function that is continuous and is defined on all the x values of its domain. The second step is finding if there is any horizontal or vertical asymptotes. Since this isn't a rational function and is continuous, there are no horizontal or vertical asymptotes. The third step is find the intervals of increase and decrease. To do so, we find the first derivative, which is f prime of x is equal to 6x squared plus 18x minus 24. Then we set the first derivative equal to 0 to find the critical points. We have a simple trinomial, so we use the man method to find the x-intercepts, which are x is equal to -4 and x is equal to 1. Now we put these critical points on a number line to visualize the intervals. Usually the number line is used when there are many critical points, so it can make it easier to organize the intervals. Now our intervals are negative infinity to -4, -4 to 1, and 1 to infinity. We put these intervals in the interval chart, where we will determine whether the function is increasing or decreasing on each of these intervals by subbing a test number on each interval into the first derivative. And if it's negative, then the function is decreasing. If it's positive, then the function is increasing. I will choose -10, 0, and 10 as my test points. When these are subbed into the first derivative, we get that the value is positive on the first and last interval and is negative on the second interval. So the function is increasing on the first interval, then decreasing on the second, then increasing on the third interval. Therefore, our intervals of increase are negative infinity to -4 and 1 to infinity, and our intervals of decrease are -4 to 1. The fourth step is finding the maximum and minimum points, which occur when there is a change in the intervals of increase and decrease. Since there is a change of increasing to decreasing at -4, we have a maximum, and there is a change from decreasing to increasing at x is equal to 1, so we have a minimum. We sub -4 and 1 into the original function and get that the maximum occurs at 102 and the minimum occurs at -23. So our maximum point is -4, 102, and our minimum point is 1, -23. The fifth step is finding the intervals of concavity. To do so, we have to find the second derivative, which is 12x plus 18. Now we set the second derivative equal to 0 to find our critical points, which is only one point, and it is x is equal to -3/2. Now we put it on the number line and organize our intervals into the interval chart. So our intervals are negative infinity to -3/2 and -3/2 to infinity. The test points will be -10 and 0, and when we plug them into the second derivative, we get a negative value on the first interval and a positive value on the second interval, which means the function is concave down on the first interval and concave up on the second interval. Therefore, the function is concave up on -3/2 to infinity and concave down on -infinity to -3/2. The sixth step is to find the points of inflection, which occur when there is a change in concavity from up to down or from down to up. And here we have a change from concave down to concave up at x is equal to -3/2. So we sub this value into the original function to get that our point of inflection happens at -3/2, 79/2, or 39.5 in decimal. The seventh and last step is to sketch the graph using all the information we found. So first we draw the graph and use an appropriate scale on both the x-axis and y-axis. We will go up and down by 1 on the x-axis, and we will go up and down by 30 on the y-axis. Next, we label any asymptotes, minimums or maximums, and points of inflection. So we don't have any asymptotes, but we have a maximum at -4, 102, a minimum at 1, -23, and a point of inflection at -3/2, 79/2. So after plotting these, we connect these points and we make sure that the function has the same intervals of increase and decrease as well as the intervals of concavity. So our intervals of increase are negative infinity to -4 and 1 to infinity, which is correct on the graph. Our intervals of decrease are -4 to 1, which is also correct on the graph. The function is concave down from negative infinity to -3/2, and is concave up from -3/2 to infinity, which is correct. So this is the correct sketch for the graph of f of x is equal to 2x cubed plus 9, x squared minus 24x minus 10. Let's look at another example. So we have f of x is equal to x to the power of 4 plus 8 times x cubed plus 200. The first step is finding the domain of the function. Since this is not a rational function and the highest power is x to the power of 4, the function is continuous and there are no x values where the function is undefined. So our domain is negative infinity to infinity. The second step is horizontal and vertical asymptotes. Because this is a continuous function and not a rational function, there are no horizontal or vertical asymptotes. The third step is to find the intervals of increase and decrease. To do so, we first find the first derivative of the function, which is f prime of x is equal to 4x cubed plus 24x squared. Next, we set the first derivative to 0 to find our critical points. We factor out 4x squared, and we get that our critical points are x is equal to 0 and x is equal to negative 6. Now we put these numbers on a number line to make our interval chart, and the intervals will be negative infinity to negative 6, negative 6 to 0, and 0 to infinity. Now we will use test point to determine the behavior of the function within that interval. We sub these test points in the first derivative, and if the first derivative is negative, then the function is decreasing. If the first derivative is positive, then the function is increasing. So we will use the test points negative 10, negative 3, and 10. If we sub in these test points, we get negative for the first interval and positive for the next two. So our intervals of increase are negative 6 to 0 and 0 to infinity, and our intervals of decrease are negative infinity to negative 6. The fourth step is finding the minimum or maximum points, which only occur when the function switches from increasing to decreasing or from decreasing to increasing. In this case, the function only changes at negative 6, changing from decreasing to increasing, so we have a minimum. So we will sub negative 6 into the original function to get that the minimum value of the function is negative 232. Therefore, the minimum occurs at the points negative 6, negative 232. The fifth step is finding the intervals of concavity. To do so, we find the second derivative, which is 12x squared plus 48x. Then we factor out 12x, and we get that the critical points are x is equal to 0 and x is equal to negative 4. Then we draw the number line to visualize our intervals. We get that our intervals are negative infinity to negative 4 to 0, and 0 to infinity. Now we use test points like negative 10, negative 3, and 10. You do not have to choose the same test points as the first derivative chart. You just have to choose any point within the interval, and you cannot choose the critical points as test points as they will just result in 0. So when we plug these numbers and we get positive, negative, positive, which means that the function is concave up on the first interval, then it is concave down on the second interval, and finally is concave up on the last interval. So therefore, the function is concave up on negative infinity to negative 4 and on 0 to infinity, and the function is concave down on negative 4 to 0. The sixth step is find the points of inflection, which happen there is a change of concavity on the critical points, such as concave up to concave down or concave down to concave up. Looking at the chart, we see that the concavity changes at both critical points, negative 4 and 0. So we sub these values into our original function to get that our points of inflection are negative 4, negative 56 and 0, 200. The last step is to use all the information we found to sketch the graph. So first of all, we draw the graph using appropriate scales on both the x-axis and y-axis. So we will go up and down by 2 on the x-axis and by 50 on the y-axis. Next, we will plot our minimum or maximum points, points of inflection, and any horizontal or vertical asymptotes. So have a minimum at negative 6, negative 232, and an inflection point at negative 4, negative 56, and another inflection point at 0, 200, and we have no asymptotes. Next, we connect these points together, and we make sure that the intervals of increase and decrease as well as the intervals of concavity match the graph. So yes, the function is decreasing from negative infinity to negative 6, and increasing from negative 6 to infinity. The function is indeed concave down from negative 4 to 0, and is concave up from negative infinity to negative 4 and from 0 to infinity. So this is the correct graph sketch for the function f of x is equal to x to the power of 4 plus 8x cubed plus 200. Let's look at another example. We have g of x is equal to x squared divided by x squared plus 9. The first step is to find the domain. Since this is a rational function, we look at the denominator of the function and set it equal to 0 to see what values will make it equal to 0, because if the denominator is 0, then the function is undefined at that x value, meaning the domain is not continuous as there will be a vertical asymptote. However, if we make x squared plus 9 equal to 0, and we move the 9 to the other side to get x squared is equal to -9, we cannot square root a negative number because they will be imaginary numbers that are undefined. This means there are no x values that make the denominator equal to 0. So our domain is -infinity to infinity. The second step is finding if there is any vertical or horizontal asymptotes. Since the domain is continuous, there are no vertical asymptotes, but there is a horizontal asymptote, which we can find by looking at the highest degree of the function for the x values within the function and ignoring all the constants. So we will be left with x squared over x squared, which is simply just 1. So we have a horizontal asymptote at y is equal to 1. The third step is to find the intervals of increase and decrease. To do so, we find the first derivative. Since this is a rational function, we use the quotient rule to find the first derivative. So g prime of x is equal to 2x times x squared plus 9 minus x squared times 2x divided by x squared plus 9 squared. We simplify to get that the first derivative is equal to g prime of x is equal to 18x over x squared plus 9 squared. Now set this equal to 0 to find the critical points. Since we only need the numerator to equal 0, we make 18x equal to 0, and if we divide it by 18 on each side, we get that our critical point is x is equal to 0. Now we put 0 on the number line to find that our intervals are -infinity to 0 and 0 to infinity. We will use -1 and 1 as test points, and when we plug these into g prime of x, we get a negative value for the first interval and a positive value for the second interval, which means the function is decreasing on the first interval and increasing on the second. Therefore, the intervals of increase are 0 to infinity, and the intervals of decrease are -infinity to 0. The fourth step is finding maximums and minimums. Since there is a change from decrease to increase at x equals 0, we sub in 0 into the original function to find that we have a minimum at the 0, 0, which is the origin. The fifth step is finding the intervals of concavity. To do so, we find the second derivative by using the quotient rule again. So we get g double prime of x is equal to 18 times x squared plus 9 squared minus 18x times 2 times x squared plus 9 times 2x divided by x squared plus 9 squared, squared again. To simplify, we can factor out the x squared plus 9 from the numerator and cancel it with one of the x squared plus 9 to the power of 4 in the denominator. After simplifying, we get that g double prime of x is equal to -54x squared plus 162 divided by x squared plus 9. Now we set the numerator equal to 0 because if the numerator is 0 then the whole function is 0, and we get 0 is equal to -54x squared plus 162. We move -54x squared to the other side and simplify to get that x is equal to positive and negative square root of 3. Now we put them on the number line to get that our intervals are -infinity to negative square root of 3, negative square root of 3 to square root of 3, and square root of 3 to infinity. We will use the test points -10, 0, and 10, and when we sub them into g double prime of x, we get that the first and last interval get a negative value, and the second interval gets a positive value. This means that the function is concave down on the first interval, then concave up on the second interval, then concave down on the third interval. Therefore, the function is concave up on negative square root of 3 to square root of 3, and is concave down on -infinity to negative square root of 3 and square root of 3 to infinity. The sixth step is finding the points of inflection, which occur when there is a change of concavity, so we sub in negative square root of 3 and positive square root of 3 into the original function to get that the points of inflection occur at negative square root of 3, 1 over 4, and positive square root of 3, 1 over 4. The seventh and last step is to sketch the graph using all the information we found. So first we will draw and label the graph. We will go up and down by a scale of 1 on both the x-axis and y-axis. Next, we will put our horizontal asymptote at y equals 1 and minimum point at the origin, then the two inflection points at negative square root of 3, 1 over 4, and positive square root of 3, 1 over 4. Now we connect these points, and we make sure that they match the intervals of increase and decrease as well as intervals of concavity. So our intervals of increase are 0 to infinity, and intervals of decrease are -infinity to 0, which are correct on the graph. Then the function is concave up on negative square root of 3 to positive square root of 3, and concave down on -infinity to negative square root of 3 and positive square root of 3 to infinity, which is also correct on the graph. So the sketch of the graph of g of x is equal to x squared divided by x squared plus 9 is correct.